Hey guys, so I want to talk to you about some ideas from 7.2. Last time we left off with this formula that talked about how you define the surface area of a parametrized surface. Remember that all the pieces that we used here where we had so this is sort of where I'm reorienting you if you're not watching these immediately one after the other. And of course, everyone's just watching them all in a row because that's the way you do math, right? Remember that our basic machinery here is going to be this new page. So we're dealing with parametrized surfaces. So remember, for a parametrized surface, we have a domain D, which is sort of our domain. It consists of coordinates S and T. We have an X, which is a function that takes the domain into R3. A surface has to be in three-dimensional space. It doesn't make any sense for a surface to sit in R2. We can do things in R4, but that requires like lifting a bunch of definitions that you probably don't really want to do. We defined the notion of the coordinate curves. So TS and TT, these are equal to the coordinate curves, or coordinate tangents, coordinate curve tangents. We talked about the standard normal vector, N, the standard normal vector. And it's equal to TS cross TT. And remember that the picture that I want you to keep in mind when we're looking at this is you have some surface, you have some curves on it, you have a tangent that's poking out this way, maybe this is TS, and you have a different tangent that's poking out this way, which is TT. And then you look at the normal vector N, which is equal to TS cross TT. Of course, these are all vectors, and so I should be putting vectors on top of them. The last thing I'll say is remember that we use coordinate maps, right? So the way you get TS and TT is you take partial derivatives of X. So TS is equal to dx ds dsi plus dy ds dx ds I plus dy ds j plus dz ds k. And tt is equal to dx dt I plus dy dtj plus dz dtk. And this is where we think of our x as being equal to x of s and t, y of s and t, z of s and t. Extra parentheses in here. Okay, so that's sort of all the pieces that we need for the background for our differentiable surfaces. So now what we're going to do is we're going to think about how would we make a notion of scalar and line surface integrals. This is 7.2. Scalar and line surface integrals. And we're going to think about the scalar integrals in exactly the same way that we thought about scalar integrals in the line case. Sorry, that's not supposed to be scalar and line, scalar and vector. Scalar and vector surface integrals. What we're going to do is we're going to think about this in precisely the same way that we thought about scalar integration against a line, where we think about a scalar function as giving us some sort of density. And what we're doing is we're adding up the density over not length this time. So it's not a linear density, it's an area density. And that's the easiest way to motivate the definition. So if we think about a scalar function, f, and what does f do? F looks at some point in the plane. So f looks, or in 3 dimensions, f looks at an s naught t naught. So it looks at some point on the surface and says, this spits out a density at x of s naught t naught. And so essentially what we're going to do is we're going to think of a surface. We're going to break it up into a bunch of pieces. What f is going to do is it's going to assign a value to each one of those pieces. So maybe this spits out f of ck, and this is f of ck plus 1, and this is f of ck plus 2. And then it's going to multiply those densities by those areas. So the value of this particular area is going to turn out to be, I mean, you can imagine the area of each one of those rectangles. So we'll call change in AK is the sort of area of the piece AK. And so as we go piece to piece, we get different masses, right? Because we're multiplying a density function times an area, so we get a mass out. And so what we're going to say is that like the total mass of this thing, the mass of what, you know, the surface should be equal to the sum of the value that f assigns to each point in one of those rectangles times the area of that rectangle. And we've made this move a bunch of times already. In fact, we came up with an expression that measures how big one of these pieces should be. How do we get the pieces? Well, it turns out that the easiest way to build that approximation is to use the coordinate curves from last time. If we think about that parallelogram as having TS sitting on one side and TT sitting on the other side, then it turns out to be the case that the area of that parallelogram is given by this. Change in AK is equal to the length of TS cross TT ds dt. That is the distortion that it took to take the little rectangle from our domain and push it over onto the surface. And so that gives us the following computation. This is equal to, sorry, is about equal to this. And then if we take the limits and we make things really small, it should be equal to this. And what did we do to start with? This thing is supposed to be our natural notion of the double integral of f against little tiny areas. So our conclusion is that this expression that we've come up with for cutting the surface up into little pieces, these ds pieces, which mean parametrized, it's these guys, right? Little parametrized chunks of the surface in terms of the domain, can be recovered with this area computation by thinking about ds as being approximable by these little parallelograms. And so this turns out to be our definition of a scalar line integral. And so if we let x take d into R3 be smooth, let's let d be bounded, and we'll let f be continuous. Then our intuitive argument can be made concrete. The double integral over the parameterization x of f d capital S. Okay, so remember d capital S, this thing right here, d capital S is equal to the length of TS cross TT ds dt, okay, or length of n ds dt. This is equal to double integral over the domain of f of x of s and t times the length of TS cross TT ds dt. And if we really want to emphasize that we don't care about the coordinate curves and we really just care about the normal vector, the geometry of what we're doing, we could write this as the double integral over d of f of x and s and t times the length of the norm. All right, so normal vector of s and t, yes. And that's our definition of a surface scalar integral. Okay, now this should remind you a lot of how we set up the notion of a surface or of a line, a scalar line integral, right? Same kind of move. And if you remember when we did the vector version of it, we used dot products to do that. And we're going to do exactly the same thing here. We're going to use the vector dot product in order to compute how much a vector field interacts with the surface, which means we need a way of keeping track of what the surface is doing. So we're going to use the normal vector. Remember, when we were doing the line case, we had ds with no vector on top of it was the length of x prime of t dt. And when I put the vector there, it was actually the vector x prime of t dt. And the same exact move is going to happen here. We're going to have d capital S, which is the length of n of s and t ds dt. And the vector version of d capital S is the same exact move. We just deal with the normal vector itself because I want to be able to dot that with a vector field. The vector n characterizes the surface in the same way that the vector x prime of t characterizes the way that you travel down a curve. Okay, so the question that we have now is how much of a vector field passes through a surface? So in the curve case, we were asking how much does a vector field interact with a particle traveling on a path? So it's a work question. Now we're talking about a surface with an arrow going through it. And so the question is, how much of a vector field is passing through a surface? So a little picture of that would be, you have a surface, you have a little chunk of it, which you can think of as being ds, right? So we've broken up the surface into these little pieces. And then that has a normal vector attached to it, n. And sticking out of the normal vector, or maybe coming through the surface at that particular point, is some force field F or flow field. So these are all F vectors. And what I want to know is how much of the field is flowing like orthogonally, perpendicularly through the surface. And so to compute that, I'm going to be looking at F dot n instead. And that's going to be the basis for how we set up what it means to be a vector surface integral. So let's look at that as a surface. So here's our definition. So this is the vector surface integral of f along x. We define it to be the following. F dotted with d vector s now is equal to the double integral over d of f of x of s and t dotted with n of s and t ds dt. And we can actually go one step further because we could notice that we can normalize this vector. So we could write little n of s and t is equal to big N of s and t over the length of n of s and t. So we get a unit vector out. That's a unit normal. And if we do that, well, that turns this equation into, this equation then becomes the double integral over d of f x of s and t little n, there's a dot here, little n of S and T times the length of big N of S and T ds dt, but this is ds without the vector. And so we could rewrite this as the double integral over x of f dot n ds. And this is sort of the nicest version of this, because what we're saying is that I can think about sort of from our definition here, right? That this is sort of our computational formula. And this really emphasizes the geometry of the situation, which is that we don't actually care about the particular domain or parameterization that gets used. It's just the surface that we care about. And what we really care about with the surface is the normal vector. So regardless of how we parameterize the surface, once we're looking at the surface in 3 dimensions, the only thing that picks up how much of the vector field is passing through the surface is how the normal vectors point in a given direction. And so one way of thinking about an interpretation for this question, how do we interpret this? I mean, what does this mean? If I write down this, what am I doing? What am I adding up? What physical quantity can I relate this to? And the answer is we usually use the language of flux. So if we think about this as like a fluid flow, so if you imagine that F represents the flow of some fluid, water, say, and what the double integral x f dot ds is going to get you is a measure of the amount of water going through the surface and through S per unit time. So you imagine you've got some surface, it's got a bunch of normal vectors sticking out of it that describe how the surface changes direction. Those are the worst normal vectors I've ever drawn. Probably fix those. So here you've got normal vector, normal vector, normal vector, normal vector. And as the surface curves, the normal vectors curve with it. And if you have some fluid moving through it, so, you know, vectors going like this, where the vectors come and they go through the surface, then what you're computing, not all of that fluid is flowing through the surface orthogonally. Some of it's passing, some of it's going through like this, and some of this kind of flowing in this direction. So there's a flow kind of parallel to the surface and a flow perpendicular to it. And what you're doing with the dot product is decomposing that flow into the piece that's passing through and the piece that's traveling along. And that should give you some idea that the circulation theorem that we proved earlier might be true. That there's a relationship between the flow of, or the rotation, well, we can be careful here, but there's a relationship maybe between divergence and flow through. And also there might be a relationship between rotation on the surface and circulation at the edge. And that's going to be the content of the next part of the class, which is about Stokes' theorem and the divergence theorem, which is also called Gauss's theorem. But the way I want you to think about a vector surface integral is as flow of some surface or force or charge or whatever through a surface perpendicularly. Okay, so that's the point of these. I will have homework posted for these. Just some questions to get used to the idea of how these integrals work. These integrals are often more useful from a theoretical perspective than anything you're ever going to compute by hand, because you can probably already tell that the integrals are getting much harder because there's more pieces involved. You know, now we've got 3-dimensional pieces. So the surfaces have 3 functions associated with them, and the force fields have 3 vectors associated with them. There's a lot of vectors running around here. So yeah, This stuff is, again, you know, like the sort of basis of why vector analysis gets used. And next time we'll talk about what it means for a surface to be oriented. And then we'll talk about surfaces that have boundaries. We'll talk about closed surfaces. We'll talk about curl and divergence, and the curl theorem and the divergence theorem. And we'll sort of put all the pieces together, and then I guess you guys will know everything there is to know about vector calculus for the course. All right, see you for the next one.